This is ELC 131, Circuit Analysis 1. And in this video, we're going to look at the design of circuits. Now, up to this point in ELC 131, we've analyzed series circuits, we've analyzed parallel circuits, and we've analyzed series parallel circuits. But with this topic, we're going to look at the design or the synthesis of a circuit to satisfy a set of criteria. Now, this takes you to a new level of competencies in the ELC 131 class, in that design or synthesis is a higher cognitive level than, or a higher level cognitive process than analysis. So with this, you'll be progressing again to a new level of knowledge and competencies. So let's take a look at the circuit that we're going to design. And in this diagram, we see an application where we're given a source voltage of 24 volts that can deliver 1 amp of current. And we have 3 loads, load 1, load 2, and load 3. And we have to design the circuit. In other words, we have to determine the value of the resistors R1, R2, and R3 such that positive 12 volts is delivered to load 1, and load 1 will draw 500 milliamps of current from the source. Positive 5 volts will be delivered to load 2, and load 2 will draw 100 milliamps of current. And negative 12 volts has to be provided or applied to load 3, and load 3 will draw 500 milliamps of current. Now, it's not uncommon in system or circuit design that we have to provide both positive and negative voltages from a single voltage source to circuits such as amplifiers. And also that same voltage source has to deliver 5 volts to digital circuits or programmable circuits or systems such as an Arduino or a Raspberry Pi. Now, with this circuit diagram, it's oftentimes confusing to students when we talk about the fact that negative 12 volts is provided to load 3. But understand that in this circuit, current will flow from positive to negative through resistors R1, R2, and R3. And of course, when current flows down through resistor R1, there's a voltage developed across R1 that's positive to negative. When current flows down through R2, there'll be a voltage drop across R2, positive to negative. And when current flows down through R3, there'll be a voltage drop across R3, positive to negative. Therefore, the voltage at this point is negative with respect to ground, which is the same as this point. So the fact that load 3 is provided with a negative 12 volts simply describes the fact that the voltage across load 3 from here to here is negative to positive. Now, it's a bit confusing to look at this diagram and be able to visualize what's going on or to move forward with the design steps. So I've redrawn this circuit as what we more traditionally see with these loads represented with resistors. And what I've done also is I've connected all the ground points together here. I've taken load 3 that was down here and flipped it over so that the ground is up here connected to the ground that connects to load 2 and to load 1. Now, in order to determine the values of resistors R1, R2, and R3, all we have to do is apply the 3 laws that I have presented to you in the circuit, in the course, which are Ohm's law, Kirchhoff's voltage law, and Kirchhoff's current law. And these are the only 3 things we need to make use of in determining the values of R1, R2, and R3 to satisfy our design criteria. Now, the first thing we'll do is to look at the voltages that will be dropped across resistors R1, R2, and R3. And let's start down here at the bottom, and we see that resistor R3 is in parallel with load 3. And we know that parallel voltages are equal. So the voltage across load 3 is 12 volts, negative to positive. So the voltage across resistor R3 is 12 volts, positive to negative as shown. Now the voltage across load 2 is 5 volts, positive to negative, and R2 and load 2 are directly in parallel, so the voltage across R2 will be 5 volts as shown. Now, to determine the voltage across R1, we can look at 2 things. It really doesn't matter which approach we take, but we know that the voltage from here to here is 24 volts. Therefore, the voltage from here to here must also be 24 volts. And if this voltage is 12 volts and this voltage is 5 volts, then the voltage across R1 must be 7 volts. Likewise, I know the voltage from here to here is 12 volts. Therefore, the voltage from here to here must also be 12 volts. If VR2 is 5, then VR1 has to be 7. So we have the voltages across our 3 resistors, R1, R2, and R3. However, we need to find the currents through these resistors, because in order to determine the value of resistance, we have to know 2 things. With regards to that resistor, we have to know voltage and current. So in order to determine the current through these resistors, we'll make use of Kirchhoff's current law. Now we know that the current entering this node is 1 amp. And we know the current that leaves this node to flow through R1 is 500 milliamps. So we know that the current that flows through R1 must also be 500 milliamps. The current that enters a node must leave that node. Now we have 500 milliamps entering this node through R1, and we have 100 milliamps flowing this way through load 2. So that leaves us a current of 400 milliamps to flow through resistor R2. Now, looking at resistor R3, we know that we have 1 amp of current flowing back to the source. We have 500 milliamps of current flowing through load 3. So I then have to have 500 milliamps of current flowing through R3. Now we can look at this another direction because these points are all connected together. And we know flowing down through R2 is 400 milliamps. Flowing down through load 2 is 100 milliamps. So flowing down through load 1 is 500 milliamps. So flowing into this common point, this node, we have 1 amp of current. So I have to have 1 amp of current leaving that node. 500 milliamps flow through load 3, 500 milliamps flow through R3. So I can determine the value of the resistors. R1 equals VR1 divided by IR1. 7 volts divided by 500 milliamps equals 14 ohms. And R2 equals VR2 divided by IR2. 5 volts divided by 400 milliamps is 12.5 ohms. And R3 equals VR3 divided by IR3. 12 volts divided by 500 milliamps equals 24 ohms. So we were able to determine the value of these resistors by making use of Kirchhoff's voltage law to find the voltages across the resistors, Kirchhoff's current law to find the current through the resistors, and Ohm's law to determine the value of resistance once we knew the voltages and currents. So again, when faced with or when presented with a design problem such as this circuit, we only have to make use of the 3 laws, the 3 fundamental laws of electricity: Ohm's law, Kirchhoff's voltage law, and Kirchhoff's current law.